So for this problem, we're given current as a function of time equals 0 when t is less than 0, so when the time is less than 0, and this function 6e up the minus 0.2t for when the time equals 0 or goes on longer than that, to infinity. So what the question is asking is, for this equation, so this is current as a function of time, can we find charge as a function of time? And then following that, can we find the change in charge under this given time set? So from 1 second to 2 seconds. And this is the rate of charge essentially over here. So the first thing that we're going to do though is to look at the current function before we start to solve these, just to kind of understand what's going on there. So for the current function, if we draw this out, we're going to have a nice Cartesian coordinate. So we're going to have an I of t on that axis, so that's current as a function of time. And then we're going to have time on this axis. And so what we're going to look at for this one, we're going to give a little bit for the negatives, just so we have. What we have for this one is the current as a function of time before t equals 0 equals 0. So what that means is any time before this, we're going to have the current equaling 0. That one's pretty easy. Now if we plug the second part of this function in, for t is greater than equal to 0, if you plug that into your calculator, or you just remember from what these functions look like, we're going to go up to 6, because that's going to be 6 amps, just to remember the unit. And remember 6 comes out, and then we're going to have a decreasing line coming down. And that's because essentially the exponent here is negative. The e is up negative t. So that's going to bring us down. If it was up positive, it would look a little different, but this is essentially from calculus that we can remember. So this is the function. This is what the graphical representation of as current as a function of time is. So they're asking now charge as a function of time. And if you remember back from physics, we had a couple neat things with capacitors where it showed that as a capacitor was charging, as the charge got fuller, something happened to current there. And essentially, when we look at it a little more in this problem and later on with capacitors, you'll see as one goes up, kind of the other goes down. So, without ado, let's solve this problem. We're going to have Q of t as our first thing that we're solving for. So the first thing that we got to do is try to find some kind of equation that we know to be able to determine how to link these two together. How to link the current over a function of time to the charge over a function of time. And we actually do have one of those. In this chapter we have the definition of current. So current equals dq over dt. I equals dq over dt. Current equals derivative of charge over the derivative of time. Change in charge over change in time. So current, which is in amps as the unit, equals charge, which is coulombs as the unit, over second. So that's another way of the definition of current, another way to remember them if you ever mess units up. So to start with this, now we've linked essentially these two together with some kind of function of time, some change of time. So with that, now we can start to rearrange these and try to solve the integral. So what we get for the next one, we're going to just bring this out to make it a little easier. I dt equals dq. We could put that in parentheses if we want. Ooh, that was an ugly parentheses. Sorry. Anyway, we're gonna rewrite that a little bit neater. dq equals I parentheses dt. There we go. So that's the equation now that we're going to be trying to solve for. And as you can see, we have two derivatives on both sides. So what we want to do is we want to integrate both sides. So we're going to get the integral of dq equals the integral of I dt. And now we're going to try to set that up. So what are our bounds on our integral? That's the next important step. Well, if we look over here, the entire solution set is from negative infinity to infinity. However, to make this a little nicer, we can go to t, because rarely are we going to want to know exactly everything that's happening in this, so t is a very good upper bound. Why don't we use 0 as this? Because otherwise you negate this entire region, which we know it equals 0 anyway here, so we should be able to infer some things about charge about that, but we want to include this in our equation anyway. So with that being said, we're going to go from a solution set of negative infinity up to time. That's going to be our thing. So we're going to grab another one down here. Negative infinity to time of dq equals negative infinity to time of I dt with respect to time. So that's our next part of our equation. So now we can go ahead and we can do the integral of this. I'm going to integrate on this side. If we plug those in, we're going to get q of t minus q of minus infinity equals the integral of minus infinity to t of whatever the current is with respect to time. So now we have an interesting part about this. Q of t is what we're solving for in the original part of the equation. So we have that still in our equation here. Q of minus infinity. So we're going to be able to actually call that out because we know over here, if we go to minus infinity, the current is going to equal 0. And if there's no current flowing through something, there's no charge going to happen. Essentially there's no flow, so there can't be anything that's charging with that. So we know from this equation, from this 0 part, that we can cancel this piece out. So this is going to be gone. So if we rewrite that again, we're going to get charge with respect to time equals the integral of minus infinity to t of I dt. Now the last step of this is to plug what I in, what I we have, what current equation we have for the rest of the equation, because this is going to go from here to here. So if we look up here, we've got our 6e to the minus 0.02t equals the current at any time bigger than 0, so we're going to have to plug that in. So we're going to get q of t equals the integral from minus infinity to time of 6e to the minus 0.2t dt. And so that's going to be, let me close that parentheses, it's going to annoy me. That's essentially our equation that we have to integrate now. Because this side has been integrated, we have to finish it up with this side. So now we're going to integrate this. We're going to get q of t equals, remember we're going to bring this down over here, so this is going to be 6 divided by minus 0.2 e up minus 0.2 t from 0 to t. So why do we go from 0 to t? Because essentially the lower bound of this limit we took care of way up here when we got rid of that 0 part. So now we're going to go from 0 to t, because we already know everything before 0 is going to be equal to 0 from this part of the graph. So with this we can solve to plug in, so we're going to do a plug and chug, and that's going to be a q of t equals minus 30 e to the minus 0.2t from 0 to t. Then we can plug both of those in, so it's going to be q of t equals minus 30 e up minus 0.2 times 0 minus 30 e up minus 0.2 t, which is going to be our equation. So then if we solve this out here, we know that any e up to a 0 is going to be 1. So that's going to be q of t equals minus 30 minus 30 e up minus 0.2 t. And that is going to be our equation to solve for this first one, for A. What is the value of charge with respect to time of this equation? So now that we have this, this is going to be our solution set A. I'm going to put that in red real fast. This is A. We're done with the first half of the problem. Now, what we're going to do is do the second half. The second half is significantly easier. The second half we just have to do essentially the plug-in. Actually, before we do that part, we're going to plot this real fast just to kind of see what this looks like. So if we go back up here, I'm going to do another plot right underneath here of Q of t, so charge with respect to time, and then time on this one. So to make what this look like, anytime before here, again, we're going to have 0. If you don't have current flowing, you can't have something charging. That's simple. Now, with respect to this, if we plot this lovely little equation in our graphing calculator, we're going to be able to see that this essentially is a slowly increasing charge, and you're going to have a bound on that of 30 coulombs. And that kind of comes from this piece right here. You can kind of see 30 coulombs is going to come out, and that's going to be our upper bound that goes across. So with this, as you can see now just from the graphs, as the current decreases, you're going to get a charge increasing up to a point. As they kind of level off, both of them level off to their bounds. 6 amps of current to 30 coulombs here. Again, you also see the pattern that if current isn't flowing, charge isn't flowing. So we see a lot of this actually in capacitors when we're charging them up. As the current drops, the current starts dropping actually because the charge starts building on the faces inside the capacitor. So that's the conceptual idea of what we're trying to prove here. So now the second part of the problem is, what is the rate of change of charge? What is the rate of charge? So delta Q from 1 to 2. So for this one, we're going to grab out our pen again, and that's going to be our change in charge, change delta Q of T1, comma T2 equals charge at T2 minus charge at T1. Cool. Alright, so let's write that up into an equation. So this is going to be equals to the integral from minus infinity to T2 of I dt minus the integral from minus infinity of T1 I dt. So with our rules of bounds for integrals, we can change this out to equals the integral from T1 to T2 of I dt. And that's just basic calculus there, how we pulled that up. So the next step, we're going to be able to plug in now the two bounds that we have. So this is going to be equal to the integral from 1 to 2 of 6 e to the minus 0.2 t dt. So now we're going to be able to integrate that. Integral of that is going to be equal to 6e up minus 0.2 t, and they're going to pull that down to over here, minus 0.2. And then that's going to be from 1 to 2. And so that's going to equal over here, we've got minus 30 e to the minus 0.4, 2 times 2, 4, minus e to the minus 0.2. So these are numbers. So this can be solved in a calculator now, and that's going to give you equal to 4.45. And what are the units that we're using again? We're in charge. And charge, the units for charge are coulombs. So we're going to put C for coulombs. And that's the answer to this problem.